Electric vehicles are reshaping the future of transportation, offering a sustainable and efficient way to move forward. But did you know the throttle and brake system in these vehicles face challenges that could affect their reliability over time? So most EVs today use potentiometers to control the throttle and the brake input. These mechanical components, while functional, they are prone to wear and tear. Over time, this can lead to inaccuracies and increased maintenance costs, and even a whole system failure. A better alternative is by using a Hall effect sensor, a non-contact device that detects magnetic field that provides precise control by placing a magnet through its proximity to measure the flux density across the distance between the sensor and the neodymium magnet. So, as I mentioned earlier, Hall effect sensors have no moving parts, making them more reliable and long-lasting.
So, what exactly is a Hall effect sensor? When the device is placed within a magnetic field, the magnetic flux lines exert force on the semiconductor material, which deflects the charge carriers, electron, and hole to either side of the semiconductor slack. This movement of charge carriers is a result of the magnetic force they experience passing through the semiconductor material. As these electrons and holes move to either side, a potential difference is produced between the two sides of the semiconductor material by the buildup of these charge carriers. Then the movement of electrons through the semiconductor material is affected by the presence of an external magnetic field which is at the right angles to it, and this effect is created in a flat rectangular shaped material.
In linear output Hall effect sensors, as the strength of the magnetic field increases, the output signal from the amplifier will also increase until it begins to saturate by the limits imposed by the power supply. Any additional increase in the magnetic field will have no effect on the output as is it in saturation.
So here's a simple setup for the experiment to understand the sensor saturation with the varying magnet distances. So we have a neodymium magnet over here and the Hall effect sensor over here. So the goal is to measure and analyze the percentage of the saturation of the Hall sensor at different distances between the Hall sensor and the neodymium magnet. Our setup includes a Hall effect sensor connected to the Arduino and a permanent magnet attached to this L-shaped ruler. Then I use this normal ruler to adjust the distance 1 mm at a time to get the saturation of this Hall effect sensor. As a demonstration, here we have the reading of the Hall effect sensor and the percentage value as I close in the neodymium magnet against the Hall effect sensor.
Here we got a graph of the Hall effect percentage saturation against the distance. As you can see, the graph has an exponential shape. As the distance increases, the saturation percentage gets close to zero until one point it reaches the intercept of the x-axis.
Let's see how this works in a simulated application using Arduino for the EV throttle system. So we have the throttle system over here and the speedometer simulation for the EV vehicle. And for the brain of this project, it's Arduino Uno to control the position of the throttle and also the speedometer as a simulation for the EV vehicle. Initial setup. So over here, we have the Hall effect sensor and a neodymium magnet attached underneath the pedal for both the throttle and the brake. As the magnetic field strength changes, the sensor sends signals to the Arduino which adjust the servo motor position, for example the throttle and the brake, and then it responds to use the speedometer which changes proportionally to how much throttle we provide on the simulated system. So now when I press on the throttle position sensor will tell you how much I press on the throttle. At the same time, the speed of the vehicle increases. When I go full throttle, the speed of the vehicle increases gradually. And here, you can use the brakes to slow down the vehicle until to a complete stop.
The conclusion, are they reliable? So, you can see that poly effect sensors offer precision and durability as they have non-contact, non-mechanical moving parts. They have a few limitations. They're expensive. The television's potentiometers and require external power source, and the sensitivity varies within distance and the strength of the magnetic field, which could also be affected by external automatic field which are nearby to the Hall effect sensors. By replacing the potentiometer with Hall effect sensors, we can achieve greater reliability and performance, paving the way for a more sustainable future. This innovative solution not only solves the key problem but also enhances the overall driving experience.